We had methane gas, we're going to burn it, and when you say you're going to burn something, we're combining it with oxygen. We talked about, we know that's diatomic, and we have plenty of oxygen to go around, so we're going to make carbon dioxide and H2O liquid. Okay, now let's remember how we balanced this. Remember how we looked at the hydrogens? We had a 2 and a 1 and a 1. And then what do we have in front of that oxygen? What do we need there in front of the oxygen? How many? 2 or a 4? A 2. There's our balanced equation. Okay, so here I am starting section 3-2. So this is going to lay the foundation of something that's going to haunt you throughout your career here. Remember another thing I said is going to haunt you throughout chemistry? Grams to moles and back again from chapter 2. This part, doing weights, will also haunt you. So you want a good, strong foundation from today. Okay, what do these numbers mean? It can mean, and I wouldn't bother to write this down. It can mean 1 molecule of methane reacts with 2 molecules of oxygen to give us 1 molecule of carbon dioxide and 2 molecules of water. And that is absolutely true. However, that's not practical because we cannot go to the laboratory and take 1 molecule of methane, at least in our laboratory, and burn it. We got to have a slug of them, because remember we talked about molecules being so small. So these numbers also can mean 1 mole of methane reacts with 2 moles of oxygen to give us 1 mole of this and 2 moles of this. And I stick almost exclusively to talking moles here instead of molecules. Maybe a little paper and pencil problem, but it'd be worked in the very same way. So these can represent, the coefficients can represent molecules or moles, but more likely for us they're going to represent moles, because that's practical. You know, if you have a mole of something, you've got Avogadro's number. Say that number for me. Okay, good. Sounds good. But I really couldn't hear what you all said, but it sounded good to me. Anyway, 6.02 times 10 to the 23rd. Now, what these numbers never, ever, ever mean, 1 gram of that reacts with 2 grams of that. Those coefficients never, ever mean grams, or pounds, or any other weight unit. It means moles. Okay, now, let me get rid of the molecules. Okay, what if today we want to live it up? You know, just because there's 1 here, it doesn't mean we're limited. We got to burn 1 mole of that. I'm going to live it up today. I'm going to burn 2 moles of it. If I burn 2 moles of it, Nina, how much oxygen do I need?
1.
4. Yeah. Okay, if you have 1, it's going to take 2. So if I've got 2, it's going to take 4. And it makes sense. If you're burning twice as much, it's going to take you twice as much oxygen. Okay, and then we come over here. CO2. Nicole, how much? 2. And for water here, Tanya? 4. So if you double it, you got to double everything. Andrew?
How would that be worded in the problem?
Well, if you'll hang on to that idea for just a little bit, that is a weight problem. It's just about the simplest one you could have. It would be something to the effect, if I burn 2 moles of methane, how many moles of oxygen do I need? 4. And that's really a weight problem. When we work weights in just a few minutes, first of all, you've got your balanced equation. You can only deal with 2 things at a time. That's why we say weight. Now, the 2 things we deal with can be 2 reactants. It can be a reactant and a product. It could be 2 products. It could be a product going back to a reactant. But we're essentially doing that right now. I said, I'm going to burn 2 moles of this. That's the known. How many moles of this do I need? And you all fire back 4. That's a weight problem. I'm dealing with two things at a time. Okay, if I burn 2, and I have plenty of oxygen around, how much CO2 can I get? 2. That's a weight problem. First time I dealt with, this is my known, that's my unknown. The next time through, this is my known, that's my unknown. You always have a known and an unknown and a weight. Okay, but now let's go back. I don't have very much methane today. I'm going to only use 1/2 mole and burn it. If I burn 1/2 mole, Sarah, how much oxygen do I need? 1 mole. If you burn half as much, it's going to cost you half as much oxygen. So 1/2 mole of methane reacts with 1 mole of oxygen. Okay, now, new problem. I'm going to burn 1/2 mole of this, and I have plenty of oxygen. That's not an issue. How many moles of this do I get here? Antonio, what would you say?
I'm confused.
Okay, here. You got this part,
Yes.
right? 1 to 2 to 1 to 2,
The
okay?
half part I'm confused.
Okay, I got 1/2 mole.
Okay.
Now see, if we were talking molecules, I couldn't make up this problem, because you cannot have 1/2 molecule. You either got one or you don't. But if you're talking moles, because you got Avogadro's number of molecules, I can have a fraction. I got 1/2 mole of that. Let me just get rid of this garbage. Okay, if I take 1/2 mole of that, somebody told me it's going to cost us 1 mole of oxygen. Okay, you're on a roll now? So, how many moles of this would I make?
Would be half.
It would be.